Okay, so the title of the chapter is Equilibrium and Elasticity. Okay, so those are two unrelated subjects, but they generally get lumped together because that's how it's traditionally done. Equilibrium is related to your balance. Okay, that's what we mean by that. And elasticity is, you guys have all used a rubber band. You stretch a rubber band, and when you let go of the force, what happens? The rubber band comes back to its original shape. Okay? And how many times can you do that? So as long as the force is not too large to deform it or break it, it'll come back every time. That is elastic behavior. Okay? And there are many things in your body that exhibit elastic behavior, and so that's what we want to know about that. So for instance, when your heart pumps blood, your blood vessels expand, stretch, okay, to accommodate the increased flow of blood, and you want that blood vessel to come back to its original shape, like forever. Okay? It's like when you drive on a bridge. If you drive on a suspension bridge, when your car is on the bridge, what happens to the cables? The cables stretch a little, okay? And then when you drive away, you want the cables to go back to their original shape. Okay? So just like that. So there are many things in your body that exhibit elastic behavior, and we'll show you examples of that. Okay? So here's this lady. She's balanced on her tiptoe, okay? And she's in equilibrium. You will learn that this is unstable equilibrium. It takes a lot of talent to be able to do this. Okay? Now, here's a couple of things going on. You'll learn about the center of mass of the lady. And the center of mass, if you're standing straight up, is sort of your center of mass is behind your belly button. Okay? And for this lady, the center of mass is somewhere there. Okay? Now, to be balanced, what you learn is the center of mass needs to be above your footprint, directly above your footprint. Okay, so if she shakes a little and the center of mass moves to the left of the footprint, she'll topple over like that. Okay? But your brain is very smart. If she's starting to topple over, what will she do, you think? If she's starting to topple over here, she'll extend her arm and bring the center of mass back up on top. Okay, did you guys understand that? If she's toppling over this side, she'll stretch her leg that way. Okay? All right, so for her to be balanced, you'll learn the conditions for her to be balanced. Okay? By the way, so you'll learn that when you stand on tippy toe, there are parts of your body. Okay, so there are parts of your body that are experiencing 3 to 4 times your body weight. A force 3 to 4 times your body weight. Okay? So we'll learn that. Okay, so a dancer's foot withstands enormous stresses as she balances on her toe. We'll study the conditions necessary for extended objects to be in equilibrium. Okay. So if you have a point object, for it to be in equilibrium, all you need is for the sum of the forces to be 0. Okay. But for extended object, this condition is not enough. Okay. And we'll see what else is needed. So balance and locomotion are of critical importance in animals. Our bones, muscles, and tendons work together to generate forces. You guys learned in a previous chapter that our muscles generate forces, okay? And tendons store energy, okay? And produce movement or stillness. Okay, so all right. So here's another example. This guy is balanced. The weight of this guy, the gravitational force is acting down, and now we already know that. Where is the center of mass of this guy located? This system, the cyclist and the bicycle, where is the center of mass located? It has to be located right above that point of contact. We don't know where, but somewhere in there. Okay. Now what is happening? So the center of mass is somewhere there. Okay, we'll say the center of mass is there. What is the weight of this wheel trying to do? The wheel is trying to topple this guy in this direction. It's trying to rotate this guy in this direction. What is counterbalancing him? The weight of his trunk is counterbalancing it. So all this mass is in front of the pivot point. All this mass is in front of the pivot point, and his body has to be behind the pivot point to be able to balance. Okay. So the two conditions needed for equilibrium. So this force, this weight is trying to exert a torque. We call it a torque if you try to rotate an object. This weight is applying a clockwise torque, and this weight above this pivot point is applying a counterclockwise torque. So for an extended object to be in equilibrium, these two conditions must be true. And again, you don't need to remember these formulas or anything, but you need to sort of understand them. The sum of the forces on the object needs to be 0. Okay, and the sum of the torques need to be 0. Okay, so there are two forces acting on this guy. Okay. So I'll draw this. Here the weight of the guy, and there is the normal force. And those two forces need to balance. They're equal and opposite, and that's what that condition is. The torque is, this part of the weight is applying a clockwise torque, and this part of the system is applying a counterclockwise torque. And that needs to add up to 0. Okay? All right, so here's an example of elasticity. Okay, all materials have some give, even your bones give. Okay? We say that they're elastic. So for instance, when I jump, my bones compress, and now that I'm stationary, the excess force is gone, my bones stretch back to their original length. Okay? So all materials give. Okay? We say that they're elastic if you remove the force and they go back to their original shape. Like a rubber band, if you stretch, and if you let go of the force, if it goes back to its original shape, then it's elastic. Okay? If you pull on them, they stretch, and at some point they'll break, and so on. But so in your materials, you don't want to stress anything to breaking point. You don't want your tendons to rupture and stuff like that. All that will happen. When will that happen? If you apply too much force. Okay? Your bones will break if you apply too much force. We'll answer the question. So silk tends to be, so this is elastic as well. And you might have heard of this. This silk is as strong as steel. Okay? And we'll answer that question. Now, here's another property that you're interested in. So you guys might have, you've all seen springs. Okay, when you stretch a spring, you store energy in it, and when you let go, the spring goes back to its original length, and it gives back all the energy. Okay. If you take this silk fiber and stretch it, it stretches like a spring. But this guy doesn't give back all its energy. This guy gives back about 35% of its energy. All right, so the question is this less efficient than a metal spring? Why would you do that? Okay. Whenever nature does something, it does it for a very good reason. Okay, so here's the reason why it does it. It actually doesn't want to give up all its energy. You want to hazard a guess why it doesn't want to give up all its energy? Have you jumped on a trampoline? A trampoline that'll give back all its energy, it makes you jump as high as you jumped from.
Yes.
And that is fun. What is this guy trying to do? A bug comes and lands there,
Okay.
and you want to catch it. If it gave back all its energy, it'll throw the bug right back. It doesn't want to do that. So you had to design a system where you didn't give back all its energy. Okay? So it gives back only 35% of the energy. So when the bug comes back, it just gets caught and oscillates. It doesn't have enough speed to just escape. Okay? What do you think happens to the other 65% of the energy? It turns into heat. So you got to figure out, your system has to figure that out. Okay? And we'll learn about that. All right, so we'll investigate forces required for an animal to maintain balance and limits of these forces, okay, imposed by the properties of the material. So every material, there's a limit to the force you can apply to it. Okay? Injuries such as ruptured tendons and broken bones can result when these limits are exceeded. Okay? We'll learn, okay, so your bone is like, here's a model of a bone. Okay, so your bone, this is dense material. So it's like a pipe, a thick-walled pipe, and this is soft material. That's where stuff like red blood cells are made and all that kind of stuff. So this has no structural importance. All the forces are balanced here, outside. Okay? And what you learn is, your bone is, so, okay, now let me, yes. Now I'm going to draw not detail like this, okay. So now let's say I apply two forces like this. This is a compressive force on your bone. And when does this happen? Let's say when you jump and land, your bone experiences compressive force. You don't experience this kind of force too much, but there's a tensile force. What you're doing is, let's say somebody is holding onto your leg and stretching. Do you think your bone is equally strong under both conditions? So let's say I apply a 100-pound force here and a 100-pound force here. Is your bone equally strong? Meaning, if you apply this kind of force, will it break first, or this kind of force will break first? Will a tensile force break your bone first, or a compressive bone force break your bone first? Huh? Tensile will break first. Okay, so your bone is stronger under compressive forces. Okay. So here's what that means. Okay. So this is how your bones break. Okay, let's. So here's the bone. And when you apply a force like this on the bone, what happens is the bone will bend like that. Okay? Okay, so now let me draw a bent bone. You apply the force like this. What is happening to this side? This side stretched and this side compressed. So this is where the crack develops. Okay? So that's how your bone will break. All right, so this is the, so we want to learn properties of materials and stuff like that, and then we'll learn about what kind of forces will compromise structures and so on. So biomaterials, even many of those like bone that we think of, are elastic. Okay? They can compress, stretch, and bend. Their springiness allows these materials to store or dissipate energy when needed. So you saw that in this case, you had to dissipate energy. How much of the energy did you have to get rid of? 65%, okay? And you guys remember from a previous chapter, a kangaroo's tendons stored energy when it landed, every time a kangaroo jumped. And there, how much energy did it give back? 90%. Okay? So unlike this guy, which gave back only 35% there, you wanted all the energy to come back. Why did you want all the energy to be given back? So it didn't cost you as much energy to jump, hop, and go long distances. Okay? So there you want it to be efficient. All right, so we will look at an extended object. Okay. The forces on an extended object. Okay, so in this diagram, what they show you is 4 forces. They're all equal magnitude. So this is a door. You're looking at a door from the top. There's the hinge. Okay. Now, all the forces are equal magnitude. So let's say they're all 10 pounds. Will all of them be equally effective in opening the door? Can you tell if they'll all be effective? Will this force open it as effectively as this? Okay, you guys have used a wrench. The longer the wrench, easier it is to unscrew the nut. So this force, even though the magnitude is the same, this force is more effective in opening the door. Okay? This force is less effective. So what we'll learn is the torque of this force is larger. Okay? And torque, it's denoted by tau, is the force times the moment arm. So if for this force, this is the moment arm. Okay? So larger, and the moment arm is denoted by that. It's the perpendicular distance from the line of action of the force to the hinge. Okay? All right, you see, the larger the moment arm, larger the torque, and more effective it is in turning the object. Okay? So if you're applying a force like this, then the moment arm is smaller and the torque is smaller. And that's why you see when you look at the doors, all the handles on the doors are put as far from the hinge as possible. Okay? All right, so let me show you something. So you understand, oops. So look at your arm. All right. So here is the muscle attached to the bone there. The muscle is applying a force here, and there's the hinge. Okay. So to lift your arm, so here if you're lifting your arm, there's the muscle attached right there close by. And so your muscle is having to apply a large force, a very large force to lift this object. If your muscle had been attached over here, the force it would have to apply would be smaller. So in fact, you learn that the force that the muscle is applying to lift this object, so if you're lifting a 10-pound object, you're applying a force almost 10 times greater. You're applying a force of 100 pounds. To lift a 10-pound object, your muscle is applying a 100-pound force. Why would you design something like that? So it turns out that you apply forces by compressing the muscle, and the muscle can't compress too much, so it can't move too much. So that's why you're willing to apply a larger force. You'll learn that the work done is the force times distance. So input force times input distance. Output force times output distance. Okay, so what you're willing to do is you're willing to apply a large force as long as you have to move a small distance. Okay, so because your muscles can only compress small distances, that's why you are willing to apply large forces. All right, so going back here, all right, so this force is most effective in opening the door, and you saw, okay. So for extended objects, for it to be at rest, the net force and the net torque on the object must be 0. So if this object is to be at rest, all the forces acting on it must add up to 0, and the torques of those forces must be 0. Okay, so we'll we'll give you a detailed thing of the torque. Okay, so again, shown as the top view of the door that's hinged. Of the 4 forces of equal strength, they're all equal strength. Which of this will be most effective in opening the door? So the effectiveness of a force to open the door is the torque, which is F times the moment arm. Okay, for this force, the moment arm is that. For this force, the moment arm is this. For this force, the moment arm is 0 because it's going right through the hinge. For this force, the moment arm is that. Okay. So the moment arm for this force is the greatest, and that force is the most effective in opening the door. Okay. So the ability of a force to cause rotation depends on 3 factors: the magnitude of the force, the distance r from the pivot point to which the force is applied, this distance, and the angle at which the force is applied, okay, which will determine the moment arm. Okay. So if you apply a force like this, okay, again, the torque is, okay, so you can, so the torque can be written as force times the moment arm, or it can also be written as the perpendicular component of the force times the distance at which the force is applied. Okay, so in this case, here's the force. That force is broken up into this component and this component. This component is going through this component is going right through the hinge, so it won't have any, it has 0 torque. Only this component has a torque, and it's this force times this distance. Okay, so torque is the perpendicular component times the distance at which it's applied. All right, so you can also write the force, like I said, you can write it using this formula or this formula. You can use the perpendicular component and you can use that distance, or you can use the magnitude of the force and use the moment arm. Okay, so if you use the perpendicular component, this would be R. So in this formula, this is R. And in this formula, for the same setup, you can use the magnitude of the force and you would use this distance, and that's called the moment arm. Okay? So the torque is the moment arm times the force. Okay? Greater the torque. So here's Newton's second law. Forces cause mass times acceleration, and torques cause mass is replaced by moment of inertia, and torques cause angular acceleration. Okay, just like greater the force, greater your acceleration, greater the torque, greater your angular acceleration. So in your cars and trucks, they'll tell you how much torque your engine can exert. That will determine how fast your wheels can spin, and that'll determine how fast you can accelerate. Okay? All right, so let's apply this to a situation like this. Okay, so here are 2 wheelchairs. Okay, what are these people doing? They're playing basketball. And when you play basketball, what do you have to do? You got to start and stop, and when you stop, you want to accelerate as fast as possible. These people want to accelerate fast. Okay, so let's see. Torque is moment of inertia times alpha. Okay, so you want to accelerate as fast as possible, so you want to be able to apply a torque as large as possible. Okay. What do these guys want to do? They're racing. They want to go as fast as possible. Okay, and for them, okay, so let's come to these people first. You want to apply a large torque. Okay, so to apply a large torque on the wheel, okay, so here's the wheel. Here's the metal. This is the metal rim, and there's the rubber wheel. Okay, so the torque would be, this would be R, and there would be the force. Okay, so torque would be force times R. So since you want to apply a large torque, the force that you can apply is only you can apply only so much force. So this wheel where you apply the force, the rim, the metal rim, is as large as possible. This is large, so you can apply a large torque, and you can accelerate faster. Okay. So if the torque is large, then alpha will be large. Okay, so for these people, the place where you apply force, hold on to the rim, metal rim to apply force, that is large. Okay, for the racers, you see that metal rim where they're holding on and applying force is smaller. Okay, so why is that smaller? So let's look at that. You guys understand this? So let's see why this rim is smaller. Okay, so here is the metal rim where you're applying the force. Okay, now you'll see that so this is the angular velocity of the wheel, how fast it's spinning. So the RPMs of the wheel, and the speed of this wheel, and the speed of that point is R times omega. Okay, so if you applied a metal ring there, if you gave the same wheelchair as used in the basketball to a racer, what will happen? This speed, the speed of this rim is much bigger because that radius is higher. If this wheel is spinning faster, your hands are not able to keep up. When you're applying, you're trying to push the wheel, and your hands are not able to keep up. So that's why they provide a smaller wheel, smaller radius wheel, so your hands are able to keep up to be able to apply the torque. Okay. So you see, this is the kind of stuff that goes on in designing all these things. Okay. So the racer needs to move continuously at high speed, so the wheels will spin much faster. To allow his hands to keep up, his hand rims is much smaller than the chair's wheel. Okay. A basketball player needs to start and stop quickly, which requires large torques. So because you'll require large torque, that radius of that metal rim is larger. To make the torque as large as possible, the hand rim, the outside wheel that she grabs, is almost as big as the wheel itself. Okay? And you could make it bigger too, except that then the metal would be touching the floor, and you don't want that. You'd be ruining the floor. Okay. You've all experienced this. Here's another example of a torque. So if the crankshaft was directly above, so here's and if the crankshaft was directly above, you push down, you couldn't get the bicycle started. Okay, so you guys, okay, let me draw a different diagram. So if the crankshaft was there and you're pressing down on the bike, then the moment arm is small, and it's harder to get the bike started. And if the crankshaft was directly above, the moment arm would be 0, and you couldn't start the bike. When is the torque maximum? When the crankshaft is there and the wheel is there. That's when you start pedaling, then you get the maximum torque and maximum acceleration. Okay? So you get small torque here, and you get maximum torque there. Okay? So it's hard to get going if you try to start your bike with one pedal at its highest point. Okay? And that's because the moment arm is small. Your legs press almost straight down on the pedal when the pedal is near the top, and the moment arm is tiny and the torque is small. Okay? So again, if the torque is small, the angular acceleration is small, and it's hard to get it started. Okay? You achieve maximum torque and the quickest acceleration, maximum torque and maximum acceleration, if the pedal is as forward, way forward, and the crankshaft horizontal, because then the torque is this force times this moment arm. Okay. All right. Okay. Torque is a vector. Okay. And vectors have magnitude and direction. Okay. So the convention is the following. Okay. So in this case, what does this force do? So we'll look one force at a time. This force will rotate the nut counterclockwise. It'll rotate the wrench counterclockwise. What will this guy do? It'll rotate the wrench clockwise. Okay. If a torque rotates it counterclockwise, that is taken to be positive. Okay, so when a torque rotates an object counterclockwise, that is positive torque. And if a torque rotates an object clockwise, that is taken to be a negative torque. Yep. Now the direction of the torque, so it's actually, in this case, here's the application of the force, and there is the distance r. Okay. Okay. The force, the torque, the direction of the torque, so here's the crankshaft, here's the pivot point, there's the wrench, and this is the force you're applying. Okay, so the direction of the torque is perpendicular to this plane. Okay, and again, you don't have to remember this. So there's the r vector, there's the force vector. If you turn this thing, if you turn from r to the force, that gives you the direction of the torque. Okay? If you apply a force like this, r to force, the direction of the torque would be in that direction. Okay? Anyway, the direction is perpendicular to this plane, and that's all you have to remember. Okay? And the way you figure it out is when you turn from the direction of application to the force, if you use your right hand, turn your fingers from R to F, your thumb points in the direction of the torque. Okay? Torque, like a force, is a vector. The direction of the torque is perpendicular to the plane containing the force and the moment arm. Okay, so in this case, there's the force and there's the moment arm. So it's perpendicular to that plane. So it's perpendicular to this plane of this paper. A torque that tends to rotate the object counterclockwise is positive, while a torque that tends to rotate the object clockwise is negative. So this will give you a positive torque, zero torque, negative torque. Okay? So you could have a thing where there are several forces acting. Okay? So here's your force, you're pedaling down, there's the chain pulling back on the, and here's your other leg pushing down, and there's the tension in this chain, and that's the crankshaft exerting a force. Okay, and all these forces will have a torque, and so the total torque on this guy is just the sum of all the torques. Okay, so this will be a negative torque, this will be a positive torque. Okay, you're calculating the torque about this guy. About this point, this is a zero torque, this is a positive torque, negative torque, and so you can add them all up. Okay. So the forces acting on a crankshaft are shown. The net torque on the axle is the sum of the torques applied, of torques due to all the applied forces. And this sum can be positive, negative, or zero. If it's negative, it'll rotate clockwise. If it's positive, it'll rotate counterclockwise, and so on. All right, so here's a gymnast. Okay, the weight of her leg is there, of her foot is there, the weight of her lower leg is there, and so on. So weights of different parts of our body are shown. Okay. Now, when you need to calculate the torques, what you need to know is where is all her weight acting? Okay, and that is called the center of gravity. Okay, so all her weight is acting effectively at that point. That's the center of gravity. And so this weight is rotating her counterclockwise about this point. Okay, so it's got a counterclockwise torque. Gravity pulls downwards on every particle and that makes up an object, as shown for the gymnast. However, the gravitational torque can be calculated by assuming that her entire force is acting at this point. Okay? So you need to know that, and that's your center of gravity. And you need to know that for many things. So for instance, we've said this, your footprint is there, and for you to balance, what needs to be true? Your center of gravity needs to be above your footprint. Okay? If your center of gravity comes out of your footprint, you fall. Okay? So shown as the gymnast's weight acting at her center of gravity. Okay. So in this case, here's a scale pivoted at that point. Okay. When it's balanced, its center of gravity is right below the pivot point. Okay. And if you disturb it, it'll just oscillate. When the center of gravity is below the pivot point, that is a stable equilibrium. Okay. When the center of gravity is above the pivot point or footprint, that's an unstable equilibrium, because if the center of gravity comes off of that footprint, then this scale will just fall. When the center of gravity came off of the pivot, below the pivot point, it oscillated back and forth. So this is stable equilibrium, this is unstable equilibrium. So this was, so you saw that in the first image, the center of gravity for this lady was there above the footprint. So this was an unstable equilibrium. The center of gravity comes forward and she'll fall down this way. If the center of gravity went that way, she'll fall down that way. Okay. So this is an unstable equilibrium, and you have to actively rebalance all the time not to fall. Okay. All right, so this shows you, for an object like this, how to calculate the center of gravity. And again, you just, so for this object, the center of gravity is there. And the way you calculate the center of gravity is, see, for this mass, the center of gravity, x-coordinate of the center of gravity was there. So x1 times m1. And then for this mass, the x-coordinate of the center of gravity was there. x2 times m2. Okay? And then divide by the total mass, and that'll give you the x-coordinate of the center of gravity. Okay, so that's how you can calculate the center of gravity. This is, again, we won't be using this formula, but in case in the future you need it. Okay, so there is the center of gravity of the object. So here is a pike position for this gymnast. Okay, and there is his arm holding on to the ring. Okay, and for him to balance, what should be true? The center of gravity needs to be right above the footprint. Okay, is this a stable equilibrium or an unstable equilibrium? I'm sorry? See, when the center of gravity is above your footprint, this is an unstable equilibrium. If it's below the footprint, if you were hanging on with your arms up above you, then that would be a stable equilibrium. Okay? So this is an unstable equilibrium. Okay, so the gymnast in the photo is demonstrating the pike position, and you see his hands are slightly in front of his hips. His hands have to be in front of his hips because the torso is heavier and the center of gravity is higher. So he's got to make sure that his hands are below his center of gravity. Okay, what happens if he leans forward? What happens if he leans back? Then the center of gravity would come back, and he would have to pull the ring back. Okay, and so the way he's balancing is by moving his hands. And if he leans, if his foot comes down, if his legs come down, then the center of gravity will go back, and he'll have to move his hands back again. Okay. Since the center of gravity is above the pivot point, this is an unstable equilibrium configuration. Okay, this shows you the calculation of the center of gravity. Okay. So what is done is his body is broken up into two parts, the torso and the legs. There is the center of gravity of the leg, and there is the center of gravity of the torso. And so the y coordinate of the center of gravity, this guy, okay, and again, you don't have to, I'm just showing you in case you will need it in the future. The y coordinate of the center of gravity is y coordinate of the trunk times the mass of the trunk, and then y coordinate of the legs, which is 0, times the mass of the legs. And that gives you, divided by its total mass, that gives you this distance. Similarly, this formula gives you the x coordinate of the center of mass. Okay, so x coordinate of the trunk is 0, and x coordinate of the leg is that. Okay, so that gives you that. Okay, so here are the numbers for this person. Okay, that's how you would calculate the center of mass. All right, so when you're standing straight up, see there's your center of mass, there's your center of mass. Why did this center of mass is higher than this center of mass? I'm sorry? I'm sorry? Yeah, because you've extended your arm, there's more mass distributed, so that's why the center of gravity went there. Okay? Look at this. When you're bent over, see the center of mass is outside your body. Okay, this is important. So the center of mass need not be within your body. It can be outside your body. And that's what this idea is. Okay, so this is called the Fosbury flop. Okay, so in this diagram, what do you see? So this guy is doing a high jump. Yeah. I'm sorry?
I said yeah.
Okay, and is there anything that you notice?
Well, his back is to the pole.
Okay, so the idea behind this is the following. See the center of gravity, the center of mass of the object? It's going below the bar. Okay, so here's what this means. Okay, let's say, so here's a bar, and now I'm going to draw a side view. Let's say in the old days, when they did high jump, this is how they jumped high, across the bar. Okay, there was the center of gravity, and the center of gravity went above the bar. Okay, now most athletes are equally strong, and what they can do is, your strength is determined by how high you can raise your center of mass. So if you're competing, most everybody is equally strong, and so you don't win by much. Now, if you learn to jump like this is called the Fosbury flop. Your center of gravity is going underneath the bar. So now, if you're doing a Fosbury flop, you can jump over this bar because your center of gravity, you were just as strong as this guy. There's the center of gravity, but you folded yourself over the bar. Okay? So, Mr. Fosbury, he was from Oregon. In the 1968 Olympics, he he did this technique and he won the gold medal. Okay. So using the Fosbury flop, the center of gravity jumper can pass underneath the bar, and so you can clear a higher bar. So he employed this in the Mexico Olympics and won the gold in 1968. And so see, this was in 1900s. Your center of gravity is going above the bar, so there's only, and then the western roll, again, your center of gravity is going above the bar. The straddle also goes above the bar. And now everybody jumps like this. High jumps, pole vault, and everything. Okay. Whenever you want to cross a high bar, this is what you do. And because your center of gravity is going below. And look at this. So back in 1895, the high jump record was 1.9 meters. 1.9 meters is 6 feet 4 inches. So that was the record. Okay. And once the Fosbury flop started being employed, you see the records started going up. Okay. All right, so now we'll give you the condition for static equilibrium. If you have an extended object like that, if you have a point object, all you need is for these two forces to cancel each other, and all you need is this condition to be true, okay? That the sum of the forces need to be 0 for it to be in equilibrium. But when you have an extended object like this, not only do these forces need to equal and cancel each other, but if they're like this, what would happen if you apply a force like this, these forces to this object? What would happen? They're equal, the forces are canceling, but will this object be at rest? What will happen? It's going to spin. Yes, very good. So this force, there's the center of gravity, it'll spin like this. Okay? So even though the forces add up to 0, for an extended object, that condition is not enough to ensure that this is at rest. In addition, you have to have the torques add up to 0. Okay? So for an extended object to be at rest, not only do the forces need to add up to 0, the torques also need to be 0. For this object, the torques will add up to 0 as well. I mean, in fact, each force is exerting a 0 torque about the center of mass. Okay? So for an extended object, you need two conditions. This condition is the sum of the forces need to be 0, and the second condition is the sum of the torques need to be 0. Okay? So in many disciplines, it's important to understand the conditions under which objects do not move. Buildings, dams need to be designed such that they remain motionless. Joints in the body must sustain large forces when the body is supporting heavy loads. Okay. So for example, in this case, which one will be in static equilibrium? So all these forces are equal, these forces are equal. This force is twice that force. Okay, so this is twice that force, so the sum of the forces is 0 here. The sum of the forces here is 0. This here, there's a net force in that direction. Here, there's a net force in this direction. So these two guys won't be at rest. Between these two guys, which one will be at rest? What will happen to this guy? Okay, this force, you calculate the torque about this guy is rotating him counterclockwise. This guy is rotating him counterclockwise. This guy is rotating him clockwise. So this object will rotate counterclockwise. This object, this is rotating in clockwise, counterclockwise, and this has no torque. Okay, so this is balancing that. So this guy will be at rest. Okay. So sum of the torques for this guy is also 0. Okay. Sum of the torques for this guy is not 0. Okay. So this is the only object that will be at rest. All right, so here's a bucket that's being lifted. Okay. So this guy's applying a force in that direction. There's the force. There's the weight of the bucket. There's the pivot point, and the pivot point is applying a force like this. Okay. Now, so if this guy is at rest, this bucket is trying to rotate this beam counterclockwise, and this force is rotating the beam clockwise. Okay. So this is what is this? Okay. So this is the weight of the bucket. Since it's being rotating counterclockwise, that's positive. Weight of the bucket times the beam times this distance, and this is the force that the man is applying, and D is this distance. All right. For now, well, so the weight is the mass times gravity, but we'll ignore that calculation. I'll do a simpler calculation. So here's the beam, so you will understand this better. Here's the bucket, and let's say the mass of the bucket is 1,000 kgs. And let's say this distance is 2 meters. And let's say this is the force that the man is applying, and this distance is 6 meters. All right, so, and there's the pivot point. The force of the bucket is applying a counterclockwise torque. The man is applying a clockwise torque. All right, m times 2 meters, this distance, force times, and again I'll not multiply that by distance, force times 2 meters, there's the moment arm, minus the force that the man is applying times 6 meters should be 0. So the force is 2m by 6, 1/3 the mass of the bucket. Okay, so what we are saying is, if this distance is 3 times this distance, then the force you're applying is 1/3 the weight of the object. Okay, so greater the lever arm, smaller the force you have to apply. Okay, and if you're, like I said, if you're 4 times as far as this distance, you would apply 1/4 the force. Okay, that's what this is saying. Okay. And this is a simple machine. Okay. The mechanical advantage of this machine is how much force you lifted divided by the input force. So if you're applying a force that is 1/4 as great as the weight you're lifting, your mechanical advantage is 4. Okay. In your body, your muscles, the forces that you're applying, the input forces are 10 times larger than the weight you're lifting. So your mechanical advantage in your body is about 1/10. And why is that? Again, we said because your muscles can't contract too much. Okay, so they apply greater forces. Okay. So by the way, the input work is always equal to the output work in frictionless situations. When there's friction, input work is always greater than output work. Okay. So again, the greater your moment arm, the smaller the force you apply. Okay, so again, this is a machine with the mechanical advantage of 3 to 4, again, depending on how large the beam is. Larger the beam, smaller the force you would have to apply. Okay, but what's the problem with the larger beam? I'm sorry? Well, it would bend and it might break and stuff like that. All right, stability and balance. Okay, so why do athletes stand this way? It's for stability. Okay, so what do you need to do for stability? Okay, so if I'm standing like this, here's my footprint. Okay, I'm less stable. What did I just do? I increase my footprint and I'm more stable. And there's another thing I did. What did I do? I lowered my center of gravity. Okay, so if you want to be stable, what you want to do is two things. You want to lower your center of gravity, and you want to have a larger footprint. And now you see, with a 3-point stance, see your center of gravity has that much area to be above. Okay? So if you're a 4-legged animal, you're even more stable. Okay? So if we crawl on the floor, babies are more stable than when they're standing. Okay? So that's why you crawl first, because you're in a more stable configuration. Your brain needs to learn to balance before you can start walking. Okay? Because when you're walking, what happens? See, when you're walking, what happens? Each step you take, your footprint reduced. Your center of mass had to come above this leg. Your center of mass had to come above this leg. Okay? Your center of mass was moving and had to be above your footprint at all times. Okay? And that needs some calculation. Okay. All right. So the 3-point stance used by athletes in several sports is stable, not only for being like a tripod, but also lowering the center of gravity. Okay? A 4-legged quadruped is even more stable, and a quadruped can easily lift one foot off the ground, becoming a tripod without fear of falling. Okay? Here's a bird, and you see it has only 2 legs, so what does it do? It has wide feet, so it has a larger area for stability. Okay? The stability of bipeds is much more challenging because of the base of support. The area of the feet plus the area between the 2 feet are small, and so they have to be. So one solution adopted by the birds is to have very wide feet relative to their body size. So they have wide feet relative to their body size. Okay, so here's this girl. When she's standing on her flat foot, her center of mass has that much area to be above. So when she goes on tippy toe, what happens? Okay, her center of mass rose, and then the center of mass had to come forward as well, because now the center of mass has to be above her tippy toe. Okay? So the center of mass came forward and rose up. And of course, this is a much harder position because you have to keep your center of mass above that point. Okay? And so you have to constantly adjust your body. Okay? So if somebody pushed this lady from the back, what would happen? The center of mass was going that way, and what would she do? She would push her arms back to try and bring her center of mass back in spot. Okay. Humans have relatively small feet. Our stability is due to our brain's ability to constantly adjust our stance. Okay, so till kids learn that, they have a hard time walking, and it takes them about 9 months to a year to learn that. Okay. No matter what we're doing, to keep our center of gravity over quite small base of support provided by the shoulder of our feet. To maintain stability, we unconsciously adjust the position of our arms and legs. Okay, if you push her, she doesn't have to think about it. Her arms will automatically go back. Okay, so your brain is fast enough to do that. This is seen dramatically when something upsets our balance, risking a fall, and we instinctively thrust our arms or legs to change our center of gravity. Okay, so here's the gymnast. Here's the center of gravity. It has to be right above her arms. Okay? And this is an unstable equilibrium position because the center of gravity is above the footprint. Okay. Okay. So if her body tilted that way, the center of gravity would want to move this way, so she would extend her legs to bring it back like that. Okay. This is not easy to do. Okay. It takes long practice to learn to perform this remarkable feat of balance. Okay, you see this part of her torso is to the left, which is being balanced by the leg on the outside. You know. In this, among these three, which is the most stable? I'm sorry? B? Which? Okay, so for stability, there's a couple of things you want. Okay, how do you decide which is most stable? Which is the most you can tilt? Which object can you tilt the most before it topples over? That's how you decide stability. Okay, so if this is the greatest angle, then that's most stable, okay? So to find which is most stable, to be more stable, what you want is the center of gravity to be low, okay? And so this has the lowest center of gravity, and you want this to be as wide as possible. So you would have to tip this the largest before it topples over. Okay, so this is the most stable. Between these two, this has a larger center, has a larger base, but its center of gravity is higher. So you'd have to do a little more analysis. But so this is clearly the most stable. This would be the next stable, and this would be the least stable. Okay. So whenever you want to be stable, you want to have your center of gravity lower. So when you guys know tightrope walkers, when they're walking on a rope, what they have is a long pole, and the pole bends. And what the pole does is it lowers the center of gravity, and also if your center of gravity is coming off the rope, you can just lower this arm and bring it back. Okay, so you have more control. You lower your center of gravity, and you're able to bring it back on top of the rope more easily. Okay. All right, so we are going to stop here today. Okay.